In the last 3 years, something unusual has happened to the developer ecosystem. The tools we use every day, the JavaScript bundlers, the Python data processing libraries, and the Ruby web servers, are all being gutted and replaced from the inside out. This isn't just a trend or a new favorite language, it's a fundamental shift in how we think about the core of a software library. We are moving away from monolithic high-level code and toward a Rust core architecture. In this video, we'll explore why the industry is collectively deciding to rewrite millions of lines of proven code and what it means for the future of the software you build every day. It all starts with a simple observation. Our high-level languages have hit a performance ceiling that they simply cannot break through on their own.
Languages like Python, Ruby, and JavaScript were designed for developer productivity, not raw machine efficiency. They rely on two heavy abstractions: interpreters and garbage collection. As data volumes exploded over the last decade, these abstractions became bottlenecks. A garbage collector, for instance, has to stop the world to clean up memory, creating microstutters that kill performance at scale. Interpreted code is flexible, but it's thousands of times slower than the machine code your CPU actually wants to execute. When a library like Polars or SWC replaces its internal engine with Rust, it isn't just faster, it's removing the intermediary layers entirely. Rust provides zero-cost abstractions, meaning you only pay for the features you actually use, with no hidden overhead from a runtime or a collector.
The secret to this transition is the Foreign Function Interface, or FFI. Developers don't want to write Rust all day. They want the ease of Python with the speed of Rust. The Rust core strategy involves building the heavy lifting logic in a highly optimized Rust crate, then wrapping it in a thin layer of code that looks like native Python or Node.js. When you call a function in a library like Pydantic v2, your code crosses a bridge. On one side, you have the flexible, dynamic environment of your script. On the other, you have a rigid, hyper-efficient binary that processes data at the speed of the hardware. This bridge allows libraries to maintain their friendly API while achieving 10x to 100x performance gains on the underlying compute tasks. You might ask, why not C++? We've had fast languages for decades. The answer lies in safety. In a C++ core, a single memory error, a null pointer, or a double free doesn't just crash the core. It can crash the entire host language process, creating impossible to debug seg faults in your Python script. Rust's borrow checker provides a mathematical guarantee that your code is memory safe at compile time. It allows for manual memory management without the manual risk. This makes it viable to embed a high-performance core into a high-level language without compromising the stability that developers expect. You get the speed of C++ with the memory safety of Java, but without the performance tax of a virtual machine. This is the holy grail of systems programming. This architecture has led to a hub-and-spoke model for library maintainers. Instead of writing a separate library for Python, JavaScript, and Ruby, you write the logic once in Rust. This single source of truth ensures that bug fixes and performance improvements in the Rust core benefit every language ecosystem simultaneously. It's why we see projects like Apache Arrow or the Hugging Face tokenizers library dominating multiple languages at once. The engineering effort is centralized. The complexity of high-performance logic is hidden behind the familiar syntax of your language of choice. This is effectively scaling through consolidation. We are no longer building fragmented tools. We are building universal engines that plug into every platform. The results are staggering. When the Next.js team swapped their Webpack-based bundler for TurboPack, written in Rust, they saw build speeds increase by up to 700 times. When Polars challenged the incumbent Pandas library in Python, it proved that a Rust-backed engine could process data frames significantly faster while using much less memory. This isn't just about saving seconds on a build, it's about cost. For large-scale cloud services, a 2x increase in efficiency across a fleet of thousands of servers translates to millions of dollars in saved compute costs. This is why the Rust core isn't just a developer preference, it's a massive financial incentive for every major tech company.
However, this shift comes with a cost. Rust is notoriously difficult to learn, and its compile times are significantly longer than the languages it replaces. This creates a complexity tax. While the end user gets a faster tool, the maintainers face a steeper hill. Debugging across the FFI boundary, where your Python stack trace meets a Rust panic, is a unique form of developer torture. We are trading developer convenience at the library level for extreme performance at the application level. As we continue to push the boundaries of what web and data applications can do, this trade-off is becoming mandatory. We are entering an era where performance is no longer an afterthought, it's the primary feature.
The Rust core rewrite is just the beginning. As LLMs and data-intensive apps demand more from our infrastructure, the thin wrapper architecture will become the standard. We are witnessing the end of the slow software era. The next generation of tools won't just be easier to use, they will be fundamentally more efficient, safer, and cheaper to run. If you're building a library today that expects to handle high-throughput data, the question is no longer if you should use a system language, it's which part of your core you'll rewrite first. The secret is out. The most powerful software of the next decade is being built in Rust, one core at a time.